Now, hello class, welcome to uh, the presentation. Uh, we'll be explaining about dJay, which is used for enabling high density multi tenancy for cloud gaming servers with dynamic cost benefit GPU load balancing. Now, the authors for this paper were Sergey Grisin, David Chu, and Alec Wallman Roger Wattenhofer. I'm Akshay Jaitly,
I'm Priyam Patel.
and we'll be explaining about dJay and its benefits. Now, benefits of dJay in cloud gaming. dJay has several benefits in cloud gaming. It is used for utility maximization, and it is a cloud gaming server that will tune the client GPU rendering workloads dynamically. Now, by this, we mean that the GPU rendering workloads will be tuned, as in the maximum utility will be acquired based on the workloads with the help of dJay. So, the key benefits would be it ensures all clients get satisfactory frame rate, and it will also provide best possible graphic quality among clients. In order to reap the benefits, we will have to build an on-ride profiler which collects key cost data and builds a reusable regression model. So the regression model is basically used for comparison amongst the variables, the relationship among variables. Second, we use online utility optimizer, which uses regression model to tune GPU workloads for better graphics quality. Now, by this we mean that we'll make a utility optimizer which will use the regression model which has been made in the first step to tune the GPU workloads. The workloads will vary, and we'll have to have a particular system where the FPS is maintained. Now, advantages of cloud gaming. There are several advantages of cloud gaming, particularly being that the user does not need to have a high-end PC. By client-side system configuration, we mean that the user doesn't need to have a high-end configuration, and the platform compatibility issues are also eliminated as the rendering is done on the service provider end instead of the user. Now, upgrading data center servers is easier. We don't have to redeploy hardware. We don't have to change the game mechanics based on the user. So all the rendering will be done by this cloud provider. There's a vast library for players to choose and play instantly from. And there are several challenges faced by cloud gaming, it being latency, bandwidth, and multi tenancy. Now, latency is the delay between a client request and a cloud service provider's response. Bandwidth is the amount of data which can be transmitted in a fixed amount of time. And multi tenancy is an architecture in which a single instance of software application will serve multiple customers, as you can see in the diagram. Now, a single tenant will have each tenant will have a particular set of instances. Each tenant will have a single instance which it can refer from. While in this multi-tenancy system, he will be able to access multiple customers will be able to access the same instance. Now, multi-tenancy challenges faced by cloud gaming. Now, why is multi-tenant gaming challenging? You may ask. Now, it is challenging in the sense that it has GPU centric workload. Graphics rendering is reliant on the GPU. Now, continuous deadlines, 30 FPS is required for acceptable gaming interactivity. And adjustable visual quality. By that, we mean that the visual quality should be user adjustable. The user should be able to put in his own rendering settings for better and best visual quality. Now, dJay's utility. Utility helps maximize visual quality while meeting all the deadlines. There are three main functions: online utility profiling, future utility estimation, and expected utility maximization. Now, dJay collects utility measurements from live sessions and utility profile per application. A regression model is constructed. After the regression model is constructed, dJay actively monitors each session to determine whether a session's utility will change in the near term. An expected utility maximization is dj dynamically adjusts visual quality settings to deliver the best possible aggregate quality. These will be further explained in detail. GPU utilization. Now, for example, we have a virtual environment. We want to utilize GPU to the maximum. Now, static partitions of GPU for each application instance may be used for multi-tenancy. Now, however, it leads to poor server density as users come and go, making the static partitions unaccommodating. So the users are not static at a particular point, they always vary. For example, a particular gamer might be playing at this hour every day, but he might not be available at this particular instance. So the users are all changing dynamically, and it may not be able to cope up with the increase or decrease in spikes. A game's scene complexity and GPU load also vary over time. As you can see in the figure, there's a simple scene and a complex scene. The simple scene is of a room which has a barrel, and the complex scene, on the other hand, has a complex garden environment. Now, the time spans of high utilization and low utilization are indicated. So, these two scenes are varying quite a lot. Now, GPU load variance and its effects. Static partitioning must allocate conservatively for peak load since poor frame rate is unsatisfactory. This implies that during non-peak load, the GPU core sits idle. Now, as you can see, figure 1b and figure 1a. These are the two figures which were indicated in the previous slide. Figure 1b is of the complex scene and figure 1a is of the simple scene. Now, in simple scenes, the peak load is not available for a vast majority of time, indicating that the GPU cores will sit idle. If the GPU cores are sitting idle, that means there is a lot of wastage of resources, and this waste would lead to inefficient operations on the part of service providers, which will lead to massive issues in the terms of cost and benefits available to the customer as well as to the service provider. Now, rendering settings. This is a key component of gaming. As we all know, we have all played PC games and we all have had issues with rendering. So, this is a key component. Rendering settings include screen resolution, texture detail, enabling shadows, etc. Now, they are offered to users as end machines are varying greatly in capability. The users with a powerful machine may be able to handle advanced settings, while the other users would have to use a toned down version or a lower setting for maintaining the FPS. 33 millisecond per frame or 30 FPS must be the threshold for best possible gameplay without having an effect on the game logic. So even if you're altering the rendering settings, the game logic should not be affected. The game should run smoothly on the platform. Now, my friend Priyam will continue.
Yeah, so similarity score is the score that's used among the visual or video compression community, and it's basically used to detect the loss in video quality. So basically, in DJ, we're using this to compare between image with the high quality versus with the highest settings versus a distorted one, which would be with the lower settings. So here we have the range of the values that SSIM could take is between 0 and 1. Lower score would indicate that it's less fidelity to the pristine image. And the last point is showing that if you're comparing this image to itself, it has a score of 1 basically because they're the same image, so there would be no changes. And while if the images are very different, such as if it's a random noise, then when you compare them, you would get a value of 2. I mean 0. I'm sorry. Yeah. So next we'll discuss the approach taken by the authors. Um, they approach the problem in terms of cost and benefit. And cost is basically the cost of rendering on the GPU, while benefit is in terms of getting the optimal visual quality for the player based on the workload. And this can be challenging because first, the graphic settings depend on the workload at hand, and workload varies greatly due to drastic change in scene complexity. So what this means is that if a player enters a new room and the scene becomes suddenly becomes quite GPU intensive, then we need to be able to handle that through DJ. Another problem is that a high quality scene not always look different than a low quality scene. So what that means is that for a player, if you have a same scene on two different settings, a low and a high, it might not make much difference to the player, and it might look the same. So it varies based on the scene itself. Next, we'll discuss how we measure cost and benefit. So instead of measuring cost in terms of the whole frame, we're attributing cost to the different objects in the frame. So here we've discussed as things like castles, houses, enemies that are part of the frame. We can attribute a certain cost to the GPU for each object. And dprof is the component of DJ that does this mapping between the objects and the GPU cost. And we're in terms of the benefit we're getting, we're comparing it using the SSIM score we discussed earlier to compare between a frame from a live session to the optimal frame with the maximum settings. And dprof will also do this mapping between the frame's SSIM to the contribution of SSIM from each objects in the frame, so we get a per object benefit measurement. Next, we'll discuss the second component of DJ, est, which does the future utility estimation. And the focus here is that we have the ability to still change settings for visual settings for the scenes that are coming in the future, rather than focusing on what's already played, such as the past or like the current scene. So and they also introduced a concept called potential object list, POL for short. They're basically the objects inside the frame that are likely to be encountered soon by the player. So, for example, if the player is playing, he's just standing, and in his field of view, you can barely see a castle in the distance. That's a good candidate for what's object is to come in the future. So it would be uh, as part of in the list of the POL, yeah, for the upcoming scene. DEST receives this POL updates from the game dynamically and makes estimates for each rendering setting to arrive at a collection of utilities, one for each rendering setting. And whatever these lists are, it will send it to the next component. So basically, to summarize, DEST will generate a bunch of results for what is expected in the upcoming scenes, but what we want to know is what decides what is the best one. So next we'll discuss DOPT, which does the optimization. Basically, it takes the bunch of results given by DEST and picks the perfect one. So DOPT will take the future utilities computed by DEST, and it will compute a utility maximizing assignment of the rendering settings to the session and picks the best one for this session. And it also sets it, by the way. Dopt will actually set is what the component which will actually set the settings. And now we have some requirements that are needed for DJ. And first, for any instance, we need a active object list AOL and the POL for every frame. So uh, then it uses the standard rendering data structures like octrees and KD trees, which are already maintained by the games. So basically, we use these data structures for these lists, and then use them to judge if for our computation basically. And an instance can change the rendering settings dynamically. This is straightforward because all games support these changes in settings for the as we discussed rendering settings previously. Okay, so the last component that we will discuss is DICE, deterministic instance concurrent execution. So we mentioned earlier about the SSIM score and the pristine image with the highest settings, but the question is how do we get this thing to compare it to, compare all our live sessions frames to, right? So what it does is first before we even play the game we have run two instances, a master and a slave of the same game concurrently. So what we're doing is having a master will have the highest settings and a slave will have a different setting rendering settings, and they will be provided the same inputs. So the requirement is that the game should behave deterministically given the same inputs. And this might be a problem for some modern games, but the authors mentioned that there is another around how do you call it, a fix for that, where they use some a hash seed that is used by, like, in, if you think in like random number generators. So if they have that seed, they can make sure that the game behaves deterministically, if as long as they give the same inputs to both the master and the slave. So now that we have discussed all four components of DJ, let's see how they work visually together. So initially we run the DIs, the concurrent execution. We can see that they're running, there's a master and a slave instance. They're both given the same numbers, as in they're running the same session. So same game, same inputs. So from that we generate per frame, we're generating the rendering settings and frame times, the SSIM and the active object list, and we're passing those parameters to dprof, which is the utility profiler. It will take that and generate this regression model, and from that regression model we have the rendering settings, the object ID, cost, and the benefit, and that is being passed to the dest, which will,
Estimate the utility.
yes, it will estimate the utility per frame and create potential possibilities of future. It will do the prediction for what's to come, what objects are to come in the future scenes, and it will pass those potential object lists to dopt, which will make the decision on which rendering setting is the best. And it does it for all the sessions that are all the players basically playing on that same server, and it makes those settings, adjusts them dynamically for all of them.
So in this way, online utility is maximized. I'd like to add that.
Okay, so next I'll add a way to like speed up. They're doing to speed up the process, because which is called graphical object filtering. So objects we've discussed are just the part objects that are part of the frame, right? So a game might have like a bunch of objects in a scene, and it might slow down and cause performance issues for DJ. So what they did is they applied two types of filters. So first filter is they remove some objects that are not meeting certain thresholds. So first they remove the objects which don't have a certain amount of vertex count. And vertex count, you can imagine it in a way like for a game object, you can think of it as like the thing that is made out of like geometric shapes with like points and like lines connecting to it. So not what the player sees, but how it's visually represented and stored inside the game logic. So whichever objects that have less vertices, we want to not care about them because they have the least impact on the GPU load. We want to only look at the ones that are lots of vertices, and we want to see how they impact the game. So that's the first filter, and that's just the coarse grain filter. So we want to do more filtering because it might not always remove a large amount of objects. So second is we'll filter objects based on the cost and weights that we'll mention, cost and benefit weights that we'll mention later on. And if they don't meet a certain threshold, we want to also drop those objects. So here's just like a proof that they showed in the paper, that this vertex based filtering is valid. So you can see that these are the objects from Doom 3, and it shows their vertex counts, and cost is in terms of the GPU frame time. And just to define frame time is just the time that a frame takes to be rendered and displayed. And here we show that the predicted cost aligns with the number of vertices in the object. So if you can see, uh, hell chain and the elevator at the right side of the graph, they have very low vertex counts. So if we have a threshold above that, we can just drop those, as they have minimal impact on the gameplay and for the future predictions. Yeah.
Future utility estimation. DEST uses the weights of linear regression from, and dprof, that's the utility profiler, forecasts the upcoming cost and benefit. Now, GCAP starts off as a guess, which leads to more accurate utility estimates. Now, costs and benefits can be calculated for each frame, and it is possible as it is very fast and quick. So, this is the way we can calculate the cost and benefit for each frame. We apply the regression model, and we're calculating for each frame using this particular formula where B cap and C cap are the benefits and costs for each frame. So this is used for estimating the upcoming cost and benefit for G cap, which is a guess. Now, expected utility maximization. Now, DOPT uses the estimated future utilities to decide on visual quality for each session. Now, if costs are expected to rise, DOPT should downgrade the sessions that give significant resource savings, as in the sessions which will be having a low loss of data should be downgraded. On the other hand, if the costs are expected to fall, DOPT should upgrade the session that gets the most visual quality improvement from the extra resources available. So basically, it's a system where DOPT will downgrade the sessions which are not going to affect the gameplay to a maximum extent and allocate those available resources. The deallocated resources will be allocated to the other ones which require extra visual quality improvement. So it's just a allocation deallocation mechanism for allowing the elements which require greater visual quality to have that extra resource available to them. So it's a resource allocation basically. And visual quality change must be graceful by DOPT in order to ensure the changes are not abrupt. So if the changes are abrupt, that means that from a simple scene to a complex scene, as previously explained, if you're changing drastically from a simple to a complex and a complex to simple within a fraction of a second, that will lead to a lot of wastage of resources, which will not be useful and beneficial for anyone in the long run. Now, optimization problem and initial assignment. Now, the assigning rendering settings to each active session so that the aggregate utility is maximized. So the main aim is to maximize the utility. This is one of the optimization problems, and it is a part of the future expected utility optimization. So marginal utility is used instead of uh, absolute utility, as we can increase of utility of one rendering setting over the least costly rendering setting of the same session. So we are comparing this current utility with an existing low cost rendering setting in the same session. So if you have a low cost rendering setting and you have a mid cost rendering setting, then we are comparing both of them. We are iteratively picking the top ranked candidate until we run out of residual capacity. And we are using a greedy heuristic. So the idea behind this heuristic is to transform a multiple choice knapsack into a version of regular knapsack problem and apply the standard greedy solution of regular knapsack problem. Now, multiple choice knapsack is a generalization of ordinary knapsack problem where the set of items is partitioned into classes. The binary choice of taking an item is replaced by selection of exactly one item of each class of items. So we are exactly getting one item from each class of items, and that's the choice which we're using in multiple choice knapsack. So this greedy heuristic helps us in making it simple as well as fast. The following explains that there's a rendering setting, and this is indicating the cost and benefit of each rendering setting. So we have a low, medium, and high. So with the this mechanism, we are picking out the top ranked candidates, and until we are running out of residual capacity. So this entire mechanism is to initially assign and solve the optimization problem in order to increase the utility. So there should be graceful change during normal operation. By graceful change, as previously explained, we mean that the changes should not be abrupt, and we run the heuristic once per epoch, where an epoch is 5 frames. So the cost and benefit are basically the average cost and benefit over the last epoch. So we protect against abrupt changes by only permitting rendering settings that are one level above or one level below the current rendering setting. So by this, we do not have any major issue. So we basically can use some rendering settings, and we can also the residual cost until and unless we can use it to guarantee normal operation. So the changes should not be abrupt. Now, it may be the case that we are unable to converge to 33 milliseconds even after several epochs. Now, for this case, we use a two-part solution called warning and critical. Now, DOPT triggers the warning condition when the total frame time is between 33 milliseconds and 40 milliseconds for if it's more than 200 epochs. So by this, we mean that warning has a longer interval since there are many instances where the utilization spikes briefly. So it is given a more interval in comparison to critical. Now by critical, the condition is triggered by DOPT when the total frame time is more than 40 milliseconds for more than one epoch. So if it's exceeding 40 millisecond frame time for at least one or more, that means that the critical condition will be triggered, which indicates that a session permanently has transitioned from a scene with low complexity to a scene with high complexity, or a simple scene to a complex scene, in simple words. In which case we have to downgrade right away to maintain a playable experience for all clients. So the thing which we are explaining, downgrading and upgrading, is basically to maintain the playable experience. So downgrading of a session means that once you are going to transition, we have to downgrade right away. Otherwise, the playable experience will be horrendous. Now, managing session churn. User churn entails both starting and ending sessions. When a session ends, resources are freed up. There's a two-step approach when a session starts. Now, adding a new session at highest possible rendering setting that fits in residual time frame. Now, in a fully loaded system, this means that the new session can only be added at the lowest rendering system. There can be cases when the setting of every session to the lowest rendering setting does not satisfy the 33 millisecond budget. So by this, we mean that the highest possible rendering setting in residual frame time, we have to add a new session. If everything fails, we have to reinitialize all the rendering settings for all sessions. So, in summary, I believe that managing the session churn is basically used for better allocation of resources, and adding a new session at a possible rendering setting. Otherwise, we can always reinitialize. Now, implementation. This is the most critical component. Now to prototype DJ, we have modified open source Doom 3 and Fable 3 to interface with Utility Profiler, DICE, DEST, and DOPT. components for modifications done by source code, and the components as standalone processes. DJ supports one game type, which is a limitation. We extended Doom 3 and Fable 3 to invoke the DJ API to receive rendering settings change commands. The data is pulled by API rather than pushed by the game to ensure minimum impact on game performance. Now, as a result, basically we are trying to pull the data from the API rather than push, because we do not want the game performance to be affected by it in any way. Now, I'll explain profiling mode. There are two modes. Profiling mode is the first. In profiling mode, the user plays normally on the best rendering setting while DJ is recording each frame number, active object list, frame time, and frame buffer. Now, for both the games, Doom 3 and Fable 3, we use the game's pre existing visible objects data structure as the basis for active object list. Now, by active object list, we mean it is a list of graphical objects used to render the frame. We save client's input stream to a buffer to support deterministic concurrent execution, as games support replay mode. Now, during replay mode, we can collect every frame's frame number, AOL, frame time, and frame buffer. Doom 3 has replay mode built in. While Fable doesn't have any replay mode built in, it has been implemented by capture and replay command line options, which can be selected at the time of enabling replay mode. Optimization mode. So, optimization mode is used to modify the game to save the potential object list to the same shared memory as used by the active object list. So, by mapping costs to graphical objects, we can estimate a cost of novel scene based on the graphical object types it contains. Now, in order to construct the potential object list for Fable 3, we use an internal method, check visibility, that determines whether a graphical object is within a given field of view. If the object is not within the field of view, we would not consider it as a potential object list. We would not put it in the potential object list. DEST reads the data from shared memory and runs the regression mode, while DOPT takes estimated utilities and updates game with rendering setting. Now, optimization mode is also very essential in enabling higher utility and also helps in updating the game with the best possible rendering setting. Now, moving on.
All right, so we've discussed all the nitty gritty details of the implementations and how DJ works. Now we'll see how what the results were and what they found. So the first thing is their regression model they found is very accurate with 15% L1 error. And the scores that they were predicting with the SSIM for the upcoming scores were very accurate. Second thing they found was that the overhead for the online profiling is only 33 milliseconds. So basically, all the extra work they're doing to do all this profiling is not costing much in terms of gameplay. The median overhead was also only 1.8 seconds for the estimation and the optimization uh, components. And the last thing they found is that the maximization for the utility provides equal or better quality than the static configurations. Basically, what that means is that since DJ is dynamically changing the rendering settings of the game throughout the gameplay, it's showing better results than having the static configurations throughout the whole game, and it's performed in best better. It basically gives better quality, and in the best case, DJ can scale up to 4 times more session than the static GPU utilization. So that shows that it's able to handle the multi-tenancy problem. The results here, we see a graph of the predicted frame time versus the actual frame time for the game Fable 3. Frame time, basically, as I explained earlier, is the time it takes for a frame to be rendered and displayed. So the lower the frame time, the better FPS you get. As seen by the orange lines, DJ is able to get much lower frame times. Um, in all cases, you can see it's towards the lower end, and that's really good for these high end graphic games. Yeah, I mean, in most cases, you see that the times it takes for the other regular game session is that you see a lot of fluctuations and a lot of frame times up to like 4 milliseconds, while DJ is keeping that to a low. As you can see by the orange lines, it's always towards like the lower ends of the sinusoidal waves you see on the graph. And these are just the rendering settings that they showed for Doom 3 and Fable 3. So you can see Doom 3, there's the high, medium, low, and they're saying that ultra is for the video quality, ultra and high and medium. These are just the settings. You can change. You can see you can change like tree details, texture, shadows, and all that. So these are what they considered for each different category that they're using for medium, high, and low as they generalize them into these three different categories. And as we go on to the next slide, we'll see that these three categories will be used to generalize the results and see which ones are how each of these different high, medium, and low settings compare to what DJ was able to accomplish with these its dynamic settings. Yeah, so here we have two graphs. The top graph is showing uh, the results of it's comparing the results of DJ with the static changes, static settings. Basically, the blue one is the all when the game is played at an all high throughout. Orange is the all medium throughout, and the low is the gray bar. And you can see that in the first part where it's one player, you can see that the SSIM score it's able to get with DJ, it's matching the score that you get when you play the game on high settings, which is really good as DJ is dynamically changing these settings. And also we can see that the FPS that DJ was able to get is also 30 FPS, as in all the other settings. And as we move to more players, we can see that 2 players and 3 players, DJ is still maintaining the 30 FPS, but it also has a higher SSIM score due to it being able to handle these different changes in scenes and automatically changing all these settings that we mentioned in the previous slide. And we can see as we move on to more and more players, we can see at 3 players, DJ is still getting slightly better score and still maintaining the 30 FPS threshold that we mentioned earlier. So, and in the case of Fable 3, in the top right, we can see same results. We're getting FPS matches in the one player, we're getting matches with the high, same score, and 2 players. And as we go on to more and more players, we're seeing that DJ is maintaining equal or better FPS and also maintains a good SIM score, which means that the game is visually pleasing. And the below graph shows that a comparison for, results for the Doom 3 and Fable 3 for simple scenes versus complex scenes. So we can see for a simple scene on high settings, medium settings, and low settings, and on DJ, we're seeing that DJ is getting the same FPS and also maintaining a good SSIM score. And for a complex scene, it's still maintaining a good score, which means it's still visually pleasing and it's still maintaining the score, the FPS that we require of the game. And the same thing for Fable 3, we're saying that for a simple scene, same FPS, it's maintaining the 30, and same for a complex scene, it's able to get a decent FPS as well as maintaining a good score overall. And now we'll discuss some of the limitations that were mentioned and some additional ones that we want to mention. In the paper, they mentioned that DJ needs a large number of profiling trace data to build a good model that accurately predicts each rendering setting for the future scenes. And another thing that we'd want to mention is that the cost for cloud gaming is still very high. I saw online on certain videos for like Nvidia where their cloud gaming solutions were costing about like $25 per hour of gameplay, which can be pretty costly if you think about it. In a year, play if a player does not have a high-end PC, he could just save that money not by not playing that game, using the cloud service and just building his own high-end PC. And additionally, Akshay would like to add one more limitation.
The best price for performance GPUs are mostly mid-range. So the expense of getting such GPUs in the server, maximum possible performance GPUs, will also be very difficult. Now, another thing is rendering demands have increased with GPU performance boosts for the past 2 decades, and they'll increase in the future. So the rendering settings have increased tremendously since DJ was implemented, and it has been tested on games which are pretty much redundant in the modern era.
Also, earlier they mentioned that modifying the source code is another requirement, which is not always fine with all game developers. So that's also another limitation for it to handle all these getting the game objects from the games. So that's also another seems to be a limitation for DJ. And now we'll
Moving
move
on.
on to the next slide. I will just discuss some related work that has been done previously. Uh, the idea of changing the game settings to control the load on a GPU was introduced by another work named Kahawai. However, Kahawai does not address the problem of game server hosting density because all it did was run the game on low settings and then high settings and then use like static settings, and it did not have dynamic changes in settings as DJ does. And skew tune is um, another work that addresses the load problem of load imbalance, but this is not for gaming. This was for CPU intensive tasks such as the map reduce computations, and I guess they took some inspiration from these works to work on their DJ. So, in conclusion, we'd like to say that DJ lowers the cost by achieving up to 4 times more players playing, so tenant density over the existing approaches. So it will be more cost effective for the cloud service providers, and also it takes advantage of the observation that dynamically changing rendering settings can help to achieve frame rate targets when under load. So that's a very novel idea that you want to, uh, you know, always change the settings to make sure that we're handling these high end scenes and making sure that we're playing the game smoothly for the player. And lastly, DJ provides the optimal visual quality for when resources are available, and that's a really good quality that DJ focused on to make sure that it's always visually pleasing for the players and the FPS is always maintained.
So I would like to thank Professor in giving us this opportunity for presenting this paper. We learned a lot about DJ, cloud gaming, and also learned a bit more about rendering settings and the importance of it in gaming. And DJ was a great insight into how cloud gaming could be made feasible in the coming years. It's a step in the right direction, and hopefully, maybe by 2020, we would have a better platform which will overtake DJ and learn from what DJ did good and use those um, things and make it a much more advanced platform. Thank you.
Thank you, guys.